Okay, so today we will start with the another topic on another special architectures that we have other than that of CNNs and neural networks, which you have already studied in our earlier presentation by Professor Avik. So just a quick update on what Professor Avik was telling yesterday. So he told me to add some more part on on clarification of what he has told you guys in CNN. So what exactly he wanted to say is in the end he left the discussion on the output layer of the CNN and he was saying something on that. So he wanted me to add on top of it that if you are doing a binary cross entropy classification at the end, so it's better to use sigmoid layer there so that you will have a you will have a values that are confined between 0 and 1. But if you are using a multi-class classification setting in CNN, then you have to use softmax layer for that. So this was an additional information that he wanted me to give it to you. So please keep this in mind, like when you are doing classification. So for binary classification, you have to use sigmoid layer, whereas in case of multi-classification, you have to go for softmax. So other than that, now today we will start with the another topic in the case of deep learning. So it's basically recurrent neural networks, RNNs, and LSTM. So we will understand the basics of both these architectures, and we will see actually why we need them. Like is because we already have two important architectures which are doing most of our job. So you must have seen multi-layer perceptrons, which we also called as neural network by another name. And the second one is convolutional neural networks. So you already know these two architectures are there and they are doing most of our job. But why we want other some other architecture other than these two? So that's our main question. So can anyone answer this? Like why we want some other architecture other than these two? What's the requirement? Anyone? Okay, so I will tell you. So this is like, in most of the multi-layer perceptron or neural network type of setting. So what you do is you basically feed input X, which is basically a vector. So it's a one-dimensional vector which is fed into the neural network, and it's not it's not important that it's a vector. It's because of the geometry of the neural network which constrains your input to be a form of vector format. So neural network always require input in the form of a vector, and it will do various tasks like regression task or classification tasks. So the important key takeaway point from here is that the neural networks always take input in the form of a vector. The second architecture view which you have studied in your last lecture, here the input X is always in the form of image. So if you observe that carefully, CNNs were designed in a form because neural networks were taking always a vector, but we wanted to process images instead of always feeding a vector. So people proposed convolutional neural networks which actually takes input as an image rather than taking it as a vector, thereby simplifying our job. So here the input is in the form of image, and it produces, it performs various tasks like regression or classification, similar to that of neural networks. So these are the two architectures which you already know. But now another problem comes is like if X is a sequence. So if X is a sequence of words, then what will happen? So let us say, for example, let us say if you have this particular sequence like I am going. So now the important thing is how to deal with this type of data, because earlier the data that we had was X was a vector of strings of ones and zeros, so it was a one-dimensional vector. Here X is an image which you already know. It's like there are so many images which are of different types. So it's a two-dimensional matrix that represents an image. But now the question is, like, if you have a sequence which is saying I am going, let us say, then how to handle this type of situation where these are the sequence of words. So in order to handle these type of situations where we are handling sequence of words, what researchers have done is they actually try to convert these individual words. They actually try to convert these individual words into a code, into a vector, actually, you can say. So they try to convert each of these individual words into a vector. So they create a one-dimensional vector sequence for each of these words, and there are various ways of doing this. There are various ways of doing this conversion from the words into the vector format, and some of them I will list down here are like, for example, bag of words. Then you have average word to vector and word to vector also, and then we have TF-IDF. So these are the various techniques which are basically used for converting these words into a specific one-dimensional vector format. So for simplicity, if I assume that I will represent these words as a one hot encoded vectors. By one hot encoded vectors means I will explain you that. But if I represent these words as one hot encoded vector, then it will be something like this. You will have one here, let us say, and the rest of them will be all zeros. And then for M, it will be one somewhere in between, and then we will have all the other values of these vector will be all zeros. And for similarly for going also, you will have one somewhere, and the rest of the elements of this vector will be all zeros. So one hot encoding means one of the element will be one and the rest of them will be all zero. So this is very simple way of encoding these words into vector. So you can look into other techniques also which actually convert these words into vectors in a more efficient way. But this is very crude way of doing it, and we are not discussing these encodings. But to make explanation simple, I'm just using this one hot encoded vector as one of the techniques of for explaining the concept. So here, the dimension of this vector, please note the dimension of this vector will be d cross 1, let us say, because it's a one-dimensional vector having d rows. So its dimension will be d cross 1. Here d will be actually the size of the dictionary. So it will be size of a dictionary, and we assume ourselves in the initial stage that let the dictionary will be of 10,000 words. So this is what we have assumed ourselves. It can be anything, there is no constraint on putting the size of the dictionary as 10,000. It can be 1 million also. It depends upon your choice, like which kind of database you are working on. So right now we are saying that say our dictionary is of 10K words. So if our dictionary is of 10K words, then each of these individual vectors will be of size 10,000 cross 1. So this is basically our one hot encoded representation of these sequence of words. So now what happens is, like, we have what we have done is we have actually converted these words. We have actually converted these words into one-dimensional vector representation. If you observe carefully, we have converted these words into one-dimensional vector representation. So one can ask, any person can ask, like, once you have done this job, that is, you have converted these vectors into one-dimensional vector, so why we cannot use this neural network for this situation? Because we already know neural networks, right? So the concepts are known, the theory is well known. Then why we cannot use these one-dimensional vector sequences to train the neural network? So let us see whether, when we will use these vectors to train the neural network, whether it will work or not. So let us see that first. So let me draw a dummy neural network here. So this is one of the hidden layers. This is another hidden layer. And let us say we are doing a sentimental classification. So in sentiment classification, you have only one output node, which is either 0 where the sentiment is negative, and let us say 1 where the sentiment is positive. So if this is a situation, and here you have this neural network which is fully connected. So all these are fully connected neurons, and then you have here. So this is the thing. So now what you want is, you want to actually feed these vectors, this one, and this one individually into this particular neural network. So now the important point is, first of all, you have to take care in this sequence of words that these words are actually forming a sequence. Like I am going is making a sense. But if I write going, am I, this particular sentence will not make any sense because the words are jumbled around each other. And the third case can be am I going. So all these words are not making any sense because these words are not in a proper way, not in a proper format. So the important is the sequence has to be also maintained properly in order to fully understand the sentiment of this word. So right now, if I'm saying I am going, though it's not a sentiment analysis type of example, but you can understand that in sentiment analysis you will have some some review of any product. But right now I'm sticking to this only. So let us. So the important thing is the sequence of the words has to be in a proper format. So in order to feed this particular sequence of word into a neural network, what you have to do is you have to actually let me draw this. So you have to actually put like this. So this is one vector, this is second vector, and this is third vector. So here you will have this is I, this is M, and this is going. So the important thing is you have maintained the sequence, and each of these individual vectors are of dimension how much. Its vector is of dimension 10k cross 1. This is of vector 10k cross 1. This is a vector of 10k cross 1. So the total length of this vector, which is the input node, is let me draw chain colors here. So these are actually the nodes, input nodes. So you can see that the total length of this is 30k cross 1. This is the total length of the input node. And now what you are doing is you are actually connecting them. So you are connecting all these neurons like this. It's a fully connected stuff like a normal neural network. So in this way, what you have done is you have actually maintained the sequence. You have maintained the sequence of words, like you have maintained I am going like this. You have maintained the sequence of word by placing these vectors like this, and you have actually employed the neural network to solve this problem of sentimental analysis. So now, can anyone tell me, like, what problem this particular scenario is having? Like, if I do something like this, will it work in case of neural networks, or what problem it has? Can anyone tell? Anyone can answer this? Like, if I am using something like this, will it work or not? Okay, so first of all, a quick feedback. Am I audible? Am I audible? Okay. So the thing is, what I was asking is, if I want to, uh, if I'm putting this sequence of words into this neural network, so the important thing is, will this particular setting will work or not? So this particular setting will work, but the problem is, the tweets that you have, have review 1, you have review 2, you have review 3, and likewise you have review up to, let us say you have 100 reviews for a particular product. So for all of these reviews, you will have multiple words in that review. So, like, for example, this pizza is good. Then maybe other review will have only two words, like pizza tastes nice, something like this. You will have multiple words having for a particular review. You will have multiple words. Like, for example, here you have 4 words, here you have 3 words. Maybe in another review somebody would have written more detailed review of that pizza, so maybe it will have 10 words, and then again some other review will have 15 words, let us say. So the problem is, every time this input is changing all the time. Right now it is having only 30k as an input vector, but in this case, when you apply this particular thing into this input, then what will happen is this pizza takes nice, it tastes nice, will have a 30K. For this particular one you will have 40K, and for this one you will have how much? 10 into 10K, and for this you will have 15 into 10K. So every time your input size is changing depending upon the type of the review. Like if you have more words, review will be of larger size, and if you have small number of words in the review, then the input size will be of smaller size. So this is not allowed in case of neural networks because the size of the input is always changing. So that is one of the major concerns, that we cannot use neural network for this purpose. So the alternative can be, if somebody wants to fix this situation, then what he can do is he can say, okay, let us do one thing. Let us do a max of all the reviews that you have, like R1, R2, R3 till R100. So let us take the max of the number of words that each of the reviews have. So for example, if review R1 has 4 words, review R2 has 3 words, review R3 has 10, review R5, R100 is, let us say, 15, and somewhere in between you have 20 as one of the words having in in a review, then maximum of all this is 20. So this is the maximum. So somebody can ask, somebody can say, okay, let's do one thing. Let's let's do one thing. Let's copy this first. So somebody can say that let's do one thing here. Let's put the maximum size here. So it will be like this. So here you will have maximum size, and these are actually 20 into 10K size. So what will happen now is, like for review 1, for review 1 only 4 are there. So what you will do is, these first 4 blocks will be filled with some values, and in the review 2 only 3 words are there, so these 3 will be filled and the rest of them will be all zeros. And suppose for another ones, as the number of words increases, you will fill that block, and the rest of them you have to append it by zeros. So this means it's a sort of zero padding that you are doing, where you will fill only those blocks, like four blocks will be filled and the rest of them will be zero. Like 15 will be zero here, in this 17 will be zero, in this 20 blocks will 10 blocks will be zero, and for this no block will be zero, and this 5 blocks will be zero, and the rest 15 will be filled with the values. So in this way also you can solve the problem of neural network, where you take the maximum of the number of words that you have in the review. But can anyone tell me again what will be the drawback here if I do this type of strategy? Anyone can answer? Anyone of you? Okay, so the important thing is, once you have this zero padding concept, the important thing is in testing phase. So in testing phase, when you have this thing in your testing, what happens is the testing will have suppose for example the reviews in the testing are let us say only you have four words in the testing phase. So in 4 words in the testing phase will create problem here, because then again the size of the input is changing. So here testing phase is, it's creating a problem, because in testing you have 4 words, then these 4 words will again create a problem, because the network size will again change because of this testing phase problem. So this is basically the disadvantage of using neural networks. So what you have to do is, you have to actually fix the 2 important aspects. Like if you want to solve this problem, you have to fix the 2 important concepts. One is you have to come up with the architecture in such a way that for different length of inputs, your architecture should adapt to that length. It should not be like like every time the input constraint should not be there. The input length that you are applying should not be fixed. it has to be adaptable depending upon the different length of the inputs. And the second is the weight issue, the weights that you are using to train these parameters. What is that? For example, if you see here in this particular network, if you have a fully connected layer, then you can see the weight of this particular interconnection. Like for example, this layer has, let us say 5 neurons. So you can see the amount of weights that you have in this particular, matrix, which is, its dimension will be 5 cross 20 into 10K. So you can see the dimension of this matrix. It's a 5 row and 20 into 10K columns. So you can see the amount of parameters that you have to tune for this particular neural network in order to perform this sentimental analysis. So these number of parameters for such a small problem is, is like, it's a bottleneck. It's very difficult to, optimize these number of parameters because they are suddenly jumping to such a high value because of the length of the reviews that you have. So the architecture that you want to propose has to solve these two problems. The first problem is that different length of the inputs should not affect the architecture. Then it should be able to accept all the type of architectures, all the type of inputs, all kind of inputs of different length. And second is that the weights that you will be using to train should remain fixed. It should not change like with the length of the input. So you can see here as the length of the input changes, the weights also change accordingly in case of neural networks. So in order to solve this problem, what we come up with is the architecture which we call as recurrent neural networks. So this is the architecture that you use in this sequence of words, for sequence of words, or in case of natural language processing. This is the basic architecture, and this particular architecture we will see how it will address both these aspects of different length of the input and training of the weights, and these weights will be constant here. So let us see how we will do that. So what we have is like, for example, I am considering a binary classification task, considering a binary classification task. For example, sentiment analysis, where sentiment can be either 0 or 1 depending upon the reviews that you have. So for example, if you have a data set that is, let us say ith data set here. So you have this ith data set having xi as the review and yi is the sentiment corresponding to that review, and the value of this is either 0 or 1. So this is basically the data set that you have, and I is running from 1 to the number of data set, the number of reviews that you have in the data set. So for example, let us say if you have first review x1, which is actually given by x11, x12, x13, x14, x15. So this is basically, you can say that the review x1 has 5 words, 1, 2, 3, 4, 5. Then the second review, let us say, consists of 3 words, let us say x21, x22, x23. So this is the second review having 3 words. So let us see, the architecture that we are trying to come up with will be able to solve these different length inputs or not. So here what we do is, at time, so here what we'll do is we will have a layer of neurons like this. So let me draw it on the other page. So here let us say we have a first layer of neuron. So this is our layer of neuron, and let us say we have these neurons as let us say you have these neurons as k, let us say. Okay, and then what we will do is, for this particular neuron, we will feed one input x11. So this x11 is actually this x11 is nothing but it's the first word of this review x1. So what we are doing at time t is equal to 1, we are feeding x11 to this particular neural particular set of neurons, and and we will be feeding it like this. And the weight matrix that actually connects, this particular word with this particular, neurons having a dimension of k will be d cross k. Why d cross k? Because you already know that we have represented this x11 as a d cross 1 vector, and this particular hidden neuron is of dimension k, or specifically we can write it as, it's a dimension of k cross 1. So when you do an interconnection of the weights in between them, it will be of d cross k, and these weights are actually trainable weights. So now once you have this at time t is equal to 1, then you will have an output coming out from here. This output is like this, which is coming from this particular set of neurons, and let us say we call it as O1, and this is basically F times W of X11. So this particular thing is the output O1, which is coming from this, from this particular layer, and this is O1, and the dimension of this will be 100 cross, sorry, not 100, it will be k cross 1, because all the outputs of this particular neuron are taken from this. So this is a 100 cross 1, or k cross 1, you can say k cross 1 vector. So this is your O1. Now what happens is, now the second word will come. This is your second word, x12. So this second word will be coming, right? So at time t is equal to 2, these number of neurons will remain same. Please keep this in mind. So right now it's 5 here, so 5. Okay. So now what you will do is, you will actually feed the second word. This will be x12. So this is your second word of the review, x1, and this is at time t is equal to 2. So now what will happen is, we will actually feed this input, feed this output of the first one into this second layer, and again it will also have an output, which is we are representing by O2. And again you will have a weight matrix here W, and the size of that weight matrix will be d cross k. And the important thing to be noted here is that these weights W here and this weight W they both are same, they are not different. So if we constrain these weights to be same, then this problem of having weight, which we were discussing here, will be solved, because you are using the same weights every time for different words. So this weight and this weight are same. So now again you repeat this process. You repeat this process 5th time, because you have 5. You have how many words are there? 5 words, right? So for every word you will do this, and at the 5th stage you will have another similar thing like this. This is at your 5th stage. The number of neurons are still same, yeah. And then you have this here as x5. So this is the 5th word, and at time t is equal to 5. So here, whatever output you will get as an output, this output will be like O5, and this output will be actually passed through the sigmoid layer, and then it's given an output as y hat. And note that the there are some more weights which are connected. So let me show you here. This is another weight which is connected between the 5th word and the internal neuron layer. So it's also size d cross k. And there is one more weight here, which is we are calling it as W hat. So this weight actually is the weight that connects these particular neurons, these ones, with this ones. And the dimension of this you can check. It will be of size k cross k, because you are actually connecting the neurons which are here with these neurons. So the dimension of this will be k cross k. And similarly, here also you will have W dash, and the dimension of that will be k cross k. And here, if you observe for this particular scenario, this one where you have O5, which is connected to y hat, here the dimension will be it will be W double dash. Let us say it's W double dash, and this is the final one. Its dimension will be 100 cross, oh sorry, not 100. It will be K cross 1. Why K? Because K is having the number of neurons in the this one, and the and you have output as y hat, which is 1. So 1 is coming because of that. So the weights which are connecting these neurons with this particular output node, its value will be K cross 1. So that is important. So now one of the most important things to observe here is that these, these structures which you are seeing, you must be feeling that you will have, something like this, repetitive structure, and this is what is called as recurrent neural network. But sometimes you might feel confused that this whole structure is called as recurrent neural network. But note that this whole structure is called as recurrent neural network, but it's not a recurrent neural network. It's basically, the times that you are looking at, like, at time t is equal to 1, you are looking at this. At time t equal to 2, you are looking at this. At time t is equal to 5, you are looking at this. So actually, basically what you are doing is you are actually working on this single layer only. You are actually working on this single layer only. Every time you are feeding x11 here, and then after that at time t equal to 2 you are feeding x12, and at time t equal to 3 you are feeding x13, at time 4 you are feeding x14. So every time you are feeding your input to this layer only. You are not having any this, you are not having this kind of structure. It's just the time expansion of the recurrent neural network. So if you think that this is an RNN network, this is not an RNN network. RNN network is only this, which has only one structure, which is having only these hidden layer neurons, and the weights which are connecting the input to this hidden layer. Then you have output, and you can see here we have input also from this side also. So here we have this input and only one output. So here you will have one more input side, and this basically is the recurrent neural network. And basically what is happening is, this is, let us say, OT, the output of the first block which we were telling, and this output is actually going and is input into that same block again at time t equal to 2. So that's why it's OT minus 1, to show that, at past one unit past, whatever output is generated from the hidden layer, it's fed into the same layer, and you are getting an output OT. So that's why you may be, in the research papers, you will see something like this, having, a compact representation of this using like this. So this sign actually is showing you that this particular recurrence is coming because of this hidden layer is always repeating. It's repeating always, depending upon the time t equal to t, like how many words you have. Depending upon that, it's repeating, but this will remain the same. So it will not be like, you will have these number of layers or what. So you will think that this is one layer, this is second layer, this is third layer. It's not like that. Only one layer repeating every time in terms of time. So this is the concept of recurrent neural networks. And now the important thing is, you can see, for example, here in this part, you do not have an input from this side. So what we do is, to do a completion of this, what we do is we feed it from the input side with the vectors of 0 to start the process. So, and to complete the symmetry also. So here, when we start the process, we feed it with the vectors of zeros, and then we proceed further. So this completes the symmetry as far as this particular, structure is concerned. So now the important part is, like, right now you repeated this particular block 5 times because the first review had 5 words, 1, 2, 3, 4, 5. But in the second review, you have only 3 words. So now there is no problem here. The architecture is, basically the architecture is flexible in terms of the number of words. So right now, if you have 3 words, then what you will do is you will run this time from t equal to 1, then it will be t equal to 2, and then it will be t equal to 3, and it finishes off after that. So the important thing is, once you trained with this particular stuff, and then when you moved to x2, then you have to only do this forward propagation in time 3 times only, t1 equal to t2 equal to t3. And also note that the weights which are connecting these things, like you have w hat, w, and w double hat, all these weights are same. So they are not different, because this weight and this weight is same, this weight, and this weight is same, and this is the last weight, which is a different weight, so I am representing it by w hat, and this is same. And this is quite evident from this structure also, because if you have only one layer with w here and w hat here, and the last unit is having w double hat, then you can see that this w hat and w will always remain the same, and it will optimize every time the new sentiment or new words will come. So it will keep on the gradient descent will keep on updating these weights, which are the important weights which has to be learned. So the problem of varying input and exploding weights in case of neural network is solved using this architecture, which we are calling as recurrent neural network. So this is what the basic concept of RNN is. And this, if you have any questions related to this, you can ask. Anyone? Okay, so if there are no questions, so let me show you one important thing here. The important thing is, like, the back propagation. Because back propagation, you must be knowing that it's required to train the weights that you have in the RNN network. So for back propagation stuff, what happens is, let us consider a time recurrent neural network here. Like, let us say we are having this, like, for this is xi1, xi2, then you have xi3, then you have xi4, and then you have xi5. So here what happens is, when you, and this is basically w hat, every time this is w hat, in between you have this, and this is w, 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 and w. And here you have the softmax, or maybe sigmoid, and then followed by y hat. So the thing is, when you do the back propagation, what happens is, during the back propagation, it's important to observe one thing, that this y hat, which is over here, is strongly dependent upon this input, which is x15. This y hat is strongly dependent upon x15, but it is weakly dependent upon xi1. As you can, if you want to write these expressions, you will find out that this y hat is very weakly dependent upon this xi1, and it's basically a cascade of sigmoids or non-linearity, and then you have xi1 somewhere in between. So if you want to write the expression for y hat linking to this xi1, it will be a cascades of these sigmoids. So the important thing is, when you take the derivative of the loss with respect to w at time t is equal to 1. At time t is equal to 1 means, what you are saying is, you want to take the derivative of the loss with respect to w for this particular w here. So what happens is, when you take the derivative of the loss with respect to w for this particular weight, it happens that this particular derivative will become very close to 0. So this will be close to 0 because of this particular cascade of sigmoids which are multiplied here. And then if you take the multiple derivatives, and if you do this analysis, then you will find that there will be a vanishing gradient problem here, because of this situation where your y hat is very far away from this particular word. So the derivative will become close to 0. So this is actually the main problem in case of recurrent neural networks. So this can be avoided by modifying the architecture, and the modification of the architecture is performed using LSTMs. So LSTMs basically address this problem of vanishing gradients, where you have this problem of y hat getting completely the derivative is completely getting close to 0 at this location. So now this was a quick update on this backpropagation thing. So now what I will try to show you is the motivation for LSTM. So like for example, if you see LSTM architectures, why they have proposed this is because of the long-term dependency that you have in these type of situations which I was discussing. So long-term dependency means, like for example, if this sequence is very long, let us say you have 15 words here, and then what you observe is this y hat is actually very closely represented to very closely associated with this 15th word, but it's very weakly represented with this first word because of the reason which I have given you here. So the long-term dependency is a situation. So we want to actually maintain this long-term dependency. um, we want to retain this long-term dependency because there are situations where the decision of y hat depends upon the first word rather than the last word which we have here. In some practical situations, for example, if you have this particular statement, like Ganesh lived in India for 13 years and he loves watching movies, he is fan of drama, he is fluent in, and there is a there is a fill in the blanks here. So if you want to fill in this value, that he is fluent in what, English or Hindi. So what happens is your system should look into back by looking at this word which is India here. Then another important thing is movies. So the system should automatically judge that this person is living in India and he is watching movies, definitely he is fluent in Hindi. So this type of situation where your sequence is very big like this, and you want to predict the next word y hat. So this prediction is not immediately dependent upon in. This prediction actually depends upon the word India and movies, which actually occurred much earlier than this particular prediction of this word. So in order to address these type of situations, we have LSTM networks that actually work in providing these long term dependencies. So what we have is LSTM networks. The name is long short term memory. So the important thing is that this LSTM actually is able to retain the long term memory and short term memory simultaneously. So that's why we have this LSTM architecture. So the architecture of the LSTM is something like this. So this is the block, and what happens is you have a tth input of a review I, and then this is basically what is happening is this is having one input from here, which is actually the prediction at time t minus 1, and then you have a input, another input which is ot minus 1. So these terms which I am writing over here, that is xt, y hat t, ot minus 1, you can correlate with the RNN architecture which we have discussed earlier. So I'm keeping these conventions same. Now what happens is you actually do you concatenate these two vectors. After concatenation, what you do is you pass it through a sigma unit, and then we have a cross here, and then basically multiplication, and then we have a plus this side with sigma, and then you have a tan hyperbolic, and then you do a multiplication here, and after that here you again have a tan hyperbolic, and then a multiplication, then you have this thing, and this is the basic block that you have here. This is a y hat at time t. This is ct. This is yt. And this is actually, I think this one is this. I have to check whether this is this or not. You can also check. I forgot to put in here, but I think this is connecting here. So the important thing is, you have this architecture, which is an LSTM architecture. Here, this is basically a one gate, which we call as forget gate. So this is basically a forget gate. This particular gate is called as addition. So you are trying to do a input gate here. So it's an input gate. And then this particular gate here is called as output gate. So here, the important thing is, as time is also running close, so I just wanted to give you a quick intuition on how this particular structure is helping us to maintain the long-term dependencies. So here, if you see, if you focus on this particular path, which is this path. So let me draw it again here. So you have, CT minus 1. Then the top path is this. This is your forget gate input coming to this multiplication. Then you have plus, which is coming from the input gate. And then you have, output here, which is CT. So the important thing is, if your forget gate FT is all ones, if it is all zeros, or maybe you can say, let me not put it 0, if it is half. And if your input CT minus 1 is a vector having 2, 4, 6, and 2, 4, and 6. And if your input gate is all zeros, then what will be the answer here? Your answer will be 1, 2, 3. So this means whatever memory that you had at CT minus 1, you forgot actually half of that, and you passed half of it. That is 1, 2, and 3. So this particular forget gate is actually helping us in forgetting the part of the memory which is not required. And this particular gate is actually helping us to put in the additional information because of the current input xt which we are applying in this particular LSTM architecture. So this plus is adding extra information. By applying this input xt, whatever extra information you are getting, you are applying it through this plus gate. So if you have, let us say not 0, 0, 0, let us say if you have 0.2, 0.3, 0.5, so it will actually add to this vector and it will become 1.2, 2.3, and 3.5. So additional information can be added using this particular thing, which we are calling as input gate, and forgetting of the information can be done using this particular gate, which we call as forget gate. So there can be a situation where, this CT is not CT, it's OT minus 1, sorry. So here, the important thing is you have OT minus 1. So if, let us say, you have this all as ones, all of these as ones, and all of this as zeros, then what will happen? Then there will be a direct connection between OT minus 1 and OT. You can see this, like you multiply OT minus 1 by 111, so it will be OT minus 1. So there will be direct connection. So there is no addition of information. So there is a direct connection between OT and OT minus 1. So it's something like, ResNets. If you have studied ResNets, so you will correlate it with that, where you have, there is a direct skip connection between OT minus 1 and OT. So somewhere or the other, it's helping us in creating a skip connections. So here, in case of vanishing gradient problem, which I was discussing earlier, this one. So if we are able to create a skip connections here, so if we are able to create a skip connections here like this, then you can see you can immediately pass your gradients properly to Xi1 because of the skip connection that is created because of LSTM architecture. So if you want to calculate the back propagation, the derivative of the loss with respect to W at Y hat, then it can go like this very easily. So there is no involvement of this cascaded sigmas, which are actually creating a vanishing gradient problems. So because of these short circuit connections, you can actually go back to the first layer and can do the training fast, and the long term dependencies, which was earlier a problem in RNN, is replaced by LSTMs, where these blocks which are there, these blocks, keep this in mind that these blocks will be LSTM blocks and it will not be RNN blocks. So this is a quick and fast introduction about LSTM. So I didn't go into the details of every part because the time was less. So if you again want to, go into the details, you can watch my lectures. From there, you can see, I've gone through the details of back propagation and explained the equations also. That was not possible here in 1 hour's time. So this is my, I'm ending my presentation here. Professor Ghosh, please.
Thank you, Dr. Alad.
Thank you.
You are done?
Yes, I'm done. Yeah. Yes, there was one question that CT is same as OT. Yeah, they are same actually. That's why I replaced it. So both of them are same. Yeah.
Can you just mention your mail ID on the chat so
Yeah,
that
yeah.
anybody has any question, they can write back to you?
Right, right. So this is my mail ID.
Okay. Okay. Thank you.
Okay.
Thank
Okay.
you.
Thank you so much. Thank you.